Pervasive Computing Challenges, Systems, Data, and Design. Moderating this panel is my friend and colleague, Richard McCormack, who until quite recently was Senior Vice President of the Enterprise Business here at Fujitsu America, but has now taken on a leadership role in our marketing team, and he'll give you some more color about that. Richard's had over 2 decades of experience in the industry. He joined Fujitsu in a previous incarnation, part of the Amdahl business, and has been with us in a number of different senior positions in the product business. A little known fact about Richard is in a previous life, Richard designed video games, some of which you may find here in the History of Computer Museum. A little bit aging, but worth a look in the museum at some point. So please join me in welcoming Richard and the panelists for panel 3. Thank you.
Thank you. Thank you, Matt, very much. Appreciate that. I feel I've been upgraded to marketing from my old role, as opposed to, what did you say, Matt? Downgraded? Very rude. Transition, that's what he said. I've been upgraded. So welcome to our panel session. Straight after lunch, we'll get going. I've got 3 great and distinguished panelists with me here today, covering an entire spectrum of pervasive computing, everything from the system challenges we face through data and design. In fact, the entire life cycle of the space I think I have represented here. The panel told me there is no question that you could possibly think of that they could not answer. They were that confident. And I said, well, my experience has been this audience is pretty aggressive about things like that, so we shall see. We shall see. I'm joined here on stage next to me by Ian Stoker from Berkeley. Welcome, Ian. Ian's going to be talking about computation on massive streaming and noisy data. He'll do a little opening presentation in a few minutes and tell us all about what that means. I'm also happy to have on stage with me here Rami Brannitsky. Oh, did I nearly get that right?
You got it.
I've been practicing all morning on that one. He's from Numenta, and he'll be telling us about how that company is able to create models of data from multiple domains and perform analytics on that data. A very interesting topic for all of us. And then last, at the very furthest away from me he could possibly sit from Maya Design is Dutch Mcdonald, and he's going to be talking about some of the challenges around the design of pervasive computing devices, how to connect people and technology through that design when he comes onto that. He was so confident he has no slides. Excellent, I hear everyone say. But he does have a video he bought us to show us what's going on, in case he couldn't remember what he did, apparently. So that'll be very interesting to see that when it comes up. But with no further ado, because I think we've got a lot to talk about in this space, Ian, I'm going to hand over to you. Please give us a little better personal introduction than I did on your history and background, and then take us through what it's all about over at Berkeley.
Okay, thanks, Richard. So, should I?
Yes, you may stand at the podium or sit or walk.
I'm going to walk, so pretty restless. So, I am a faculty at UC Berkeley. I joined Berkeley in 2000. Actually, when I came at Berkeley, I was a networking systems guy. And during that time, since then, I went up in the application stack. So today, actually, for the past few years, most of my research is on building infrastructure, high-scale infrastructure for data processing. And I am part of the AmLab. I am one of the co-director of the AmLab, which AmLab, it's a big organization, it's a big lab. A stands for algorithms, M for people, M for machines or software infrastructures, and P for people. So it includes like 8 faculty, 40 students, 3 software engineers. And we build new generation of software. It's again to process huge amount of data fast. And some of the systems we build, maybe you have heard about, are Mesos, which is a platform, which is a resource management platform, which allow multiple cluster computing frameworks. We share the same cluster, which is in used on large scale at Twitter. And there's a higher level in the stack. We build a system like Spark and Shark, which are quite used by several companies today. Okay, so if you want more details, you can ask me later about myself. So today I'm going to talk about low latency computations on massive data, right? So this is a big problem we are all struggling to address. Before going into problem, let me make clear what are the challenges in addressing this problem. And there are at least three. The first one is that now we have more and more sources of data, more and more sensors. Everyone collects data. And it turns out that the data we collect grows faster than the Moore's law. So what this means that if you want to perform the same computation to get the same result, either it will be more and more expensive or it will take more and more time. Okay, the Moore's law alone will not save you here. The second one is that, again, a lot of data comes from sensors, it comes from people, and this data is dirty. It's not curated, has no schema, and typically no consistent semantics or syntax. In some sense, this dirtiness of the data makes it even more difficult to handle than the bigness of the data. And finally, once you collect this data, you don't want to ask trivial questions, actually like, run SQL queries. Maybe you want to do that, but more than that, you want to ask complex questions which require machine learning algorithms, require graph computation algorithms, like, several examples here, you want to see, is the building structurally safe from all the sensors you put in the building, right? Or you may want to learn from the sensors when there is a earthquake, maybe 20 seconds or 30 seconds earlier, that will make a lot of difference. Or is there a virus outbreak, maybe on these health bands. You get all this information, maybe you can figure out whether it's a virus outbreak. All of this is complex analysis. And of course, when you ask these questions, in many cases, you want to get an answer as soon as possible, right? Whether because you want to make a simple, a fast decision, or because you want exploratory, you want to verify multiple hypotheses, right? And just go straight, to one possible solution. We say, okay, you want to do some computation fast, why don't you put all the data in memory, right? Assume that it fits in memory, and memory is fast. Right? It's the fastest storage medium we are using today in our computers. Well, the point that it turns out that even if the entire data is in memory, you may not get fast enough answers. Why is that? Because computers have more and more memory today, right? Like a machine today can have 500 megabytes. Actually, there are servers today with 2 terabytes of memory. Just to scan this memory, you don't do any computation, just scanning it. It may take tens of seconds. And actually, the memory footprint, the size of the memory, capacity of the memory grows faster than the I/O channel, the bandwidth to the memory. So that will be worse and worse. Okay, so that's a problem. So how you get around this problem? Well, the main insight is that when you ask an answer, the answer doesn't always need to be exact. Why is that? Well, we are talking about the input that is noisy. So actually it turns out that even if your computation is exact, the answer may not be exact because the input is noisy. Right? You have calibration error. You measure the temperature. Right? You have an error right there. Okay? And the second observation here is that actually the errors are often acceptable if they are small and bounded. Today, almost anything you interact with has an error, a bounded error, which is small. So here are some examples. The best scale on the market today has an absolute error of plus minus half a pound. Now here is another one. It's a speedometer in your car. The error is 2.5% because it depends on the tire wear, the weather, the load of your vehicle, and so forth. And here, this is an insulin pump, one of the best on the market last year. So this is for it's patients who have artificial pancreases. So this is supposed, well, not is supposed, it's periodically releasing some precise quantity in insulin in the body of these patients with artificial pancreas. So even that has 1% error, okay? So, why is this observation important? Why do you care about that? It turns out that when you when you run a computation on a particular data set, and then you take a sample and you run the same computation, the error of that computation depends not on the original data set, but on the sample size. Actually, it depends, it's inverse proportional with the square root of S. Or S is the sample size. And you should know that, because for instance, when you get opinion polls, what do they tell you? They pick 1,000, a little bit over 1,000 people, and they tell you the error is plus minus 4.5%. They don't tell you what is the entire population. For good reasons, that doesn't really matter. It's a small factor in the error. You can neglect, okay? So that's the observation. So this allows new generation of scale-independent algorithms. So therefore, you have the algorithms which run on the data and doesn't depend on the original size of the data, just on the sample size. So what does this mean? Well, this means that you can trade between the latency and the accuracy of a computation, right? You want better accuracy, get a bigger sample. You want faster, use a smaller sample. Also means that this data rapid increase is no longer, so to speak, a problem, right? Because yes, the data may grow more than faster than the Moore's law, but also because Moore's law provides you more and more storage and more CPU cycles, right, per unit of time, it allows to process larger and larger samples in the same time. And actually it turns out that because of that, the Moore's law is your friend, like in many other instances, because it allows you to halve the error every 2 years, right? Using the same number of machines, right? Okay? So basically that's the main insight here. So it's again, just to summarize, today we are handling a huge amount of data, and this data is growing and growing and growing, and according to some studies, it grows faster than the Moore's law. So that's a big problem, okay? So in order to handle this problem, one solution is, instead of computing exact results, to compute approximate results. And it turns out that it's probably very acceptable in many applications, both because we already deal with a noisy data, so adding a little bit more error doesn't fundamentally change the result, right? And also because as humans, we are dealing with that all the time, although maybe we don't realize it, right? So it's acceptable. And the reason that's important is that when you compute an error, the error doesn't depend on the original data size, it depends on the sample size, okay? Of course, there are many challenges to achieve this, but I hope the message was pretty clear.
Good, Ion. Thank you very much. We'll hear more from you in a little while, but let's keep moving along. Rami, come onto the stage. Tell us a little bit about who you are and talk about your topic around models of data.
Thank you, and Ian, remind me to talk to you later, because I could take you to some of my sales calls, because this is exactly the type of conversation I'm having with my customers as well. So hi everyone, my name is Rami Branitsky, I'm the CEO of Grok, and you referred to us as Numenta.
Sir, I did.
You didn't butcher my last name, but but the company name, actually, we just changed our company name. Some of you may know us as Numenta, but we are now Grok Solutions. Glad to be here. I think that it's actually a great build-up to follow up on what Ian was talking about, because we think about a very similar domain, obviously coming from the commercial aspect of things. We focus on infusing action intelligence for fast data in machine. And when you think about the notion of action intelligence, it's think about the high velocity, rapid amount of information that flows from machine to machine, and the need to actually have machines respond in an intelligent fashion to the data that is coming in. And I'll talk to you a little bit more about what that means. Few truisms or few issues that we deal with, and I think that Jan was alluding to one of them. High velocity, the nature of high velocity data. I think one of the more overused and underdefined term in the industry today is big data. We think that the problem is not necessarily just with size, but has to do with the faster and faster velocity of the data coming in. And the issue with it is that there's tremendous amount of bottleneck in terms of processing the information and acting on the information. That expert bottleneck is one of the key challenges that we have as an industry in terms of taking action on some of these high velocity data streams. And obviously you always work against one constant, which is the time to value. Businesses cannot move fast enough. You always are pressed for more, faster, get to results, get to bottom line, get to value as quickly as possible. So these things are the dynamics in which we try to navigate. Just to illustrate the point, this is data taken from the utilities industry. And the smart meter, the advent of smart meters over the course of the last few years, when I talk to PG&E or other customers that we have, the notion of high velocity data is definitely illustrated with smart meters. Reads coming in every 5 to 15 minutes, and then they store it, and then what happens is that they have to deal with 3,000x more data that they store. Now, everyone is talking about Hadoop as an example, or in-memory databases like SAP HANA and so on. They don't solve the problem. You still have to store the data, and you still have to have someone who comes in and actually can take action, figure out which algorithm am I going to use, how am I going to extract the data, what action am I going to take. And that expert bottleneck creates a situation where in utilities you only have about 0.5% of all data being analyzed and processed. So I think it was, we discussed it later in one of the panels. What is the point of storing all that data if you don't really take action, or you can't really get to processing and analyzing and extracting the information that you need in order to take the right action? And the time to value, 3 weeks. And I was talking to some of the more sophisticated software companies in the world, and I'm not going to mention their name. It takes them about 3 weeks to build a model that serves such a high capacity data storage. So obviously this is not a sustainable solution. We need something else. We need a different approach. And this is our belief as Grok. Well, we derived our inspiration from a very unlikely source. But once I talk about it, maybe you'll realize that it is likely, which is the human brain. Your brain is the ultimate prediction engine. It's the ultimate streaming engine. When I talk to you and you look at me and you listen to me, hopefully, you have about 200 million sensors in your eyes alone that stream information to your brain in real time. And you're predicting everything I say and everything I do. If all of a sudden I switch to a different language, which I can, it will become an anomaly. So you'll realize this guy actually has a different language skills and so on. You're always learning. You constantly make predictions about what's next, and you act accordingly. And that's essentially how our software, Grok, operates as well. What we do with Grok is we look at things such as the data stream that is coming in. These streams could come from meters, vending machines, cars, servers, and so on and so forth. We're agnostic to the domain, and we automatically create models that describe the underlying data. And what we do from that point on, once you deploy it, it takes about 30 minutes to an hour to deploy it versus 3 weeks to deploy it. You can actually start getting results by way of predictions and anomaly detection. And what we do from that point on is we continuously update and modify the model. So you never have to take it offline for retraining. This is one of the more difficult things to do because world changes, especially with high velocity data streams. The world changes all the time. And if you're able to deploy something and fire and forget, so to speak, let it run and learn, this is fantastic from a TCO perspective. And last but not least, we allow you to take automated action. So again, going back to the notion of human bottleneck, many of the tasks we're talking about, the machine to machine, are too mundane for humans to actually handle. If I need to adjust the HVAC system here every 2 to 5 minutes because of temperature, occupancy, time of day, and so on, there's no operator in the world who would like to have that job or would do that job well. That's a task that you want to automate. And if you're able to predict some of these variables in advance, you can take the right action. You can allow the machine to take the right action for you. So Grok, as I mentioned, takes streams of data, creates automated modeling, and then the predictions and the anomaly detections required for the right action to take place. So we talked about that. A few of the applications that we are building with customers. One is in the energy sector. One of our largest customers is NNOC. It's the largest demand response provider in North America. And what we do is we allow them to manage highly volatile demand response, load shedding, load curtailing scenarios for Canadian customers, as an example, because Canada, some of the protocols and schedule of demand response in Canada are a bit more aggressive than here. So they needed something that can keep up and predict what's going to happen with a given customer in the next hour. So we do that well. We work with companies in predictive maintenance as well. This is something very, very interesting. We have a customer who deploys 800 windmills. These are big Siemens turbines, €1 million each. They deploy it in the North Sea. Predictive maintenance, or trying to predict imminent failure of any one of these machineries, is extremely difficult. They have one analyst who's tasked with it, and then you have to ship a crew. And obviously it's expensive, it's dangerous, and so on. You want to be able to predict how these machines are going to behave. Most of the predictive maintenance solutions in the market today are always condition-based or they're threshold-driven. So once something happens, then you take action. The key thing is, just like your car, many of the failures actually happen before the alert is triggered, and that may be too late. And so we look at the patterns of the data, the oscillation of the data, to determine if there's something wrong. And we can do it for each and every one of these windmills independently. And the reason for it, they are similar, but they're unique. Each one of them has a different angle, different wind speed, different maintenance schedule at times, so they would behave very differently. And so we try to model each and every one of them, which is, again, something you will never be able to do with human-driven analytics. We work with companies in the financial services as well for applications that have to do with trading signals, fraud detection, and so on, which lend themselves very well to what Grok is able to do. And we also work with companies in the IT space, as an example, to manage clusters, manage cloud deployments, manage data centers, and so on, where again, you want to be able to optimize your assets based on some business rules or business needs that you need to comply with. And so we're agnostic to the domain, but we see traction definitely in areas where you have these high velocity scenarios that require you to adjust very rapidly. If you need something that has to do with, I don't know, customer churn next quarter, you're probably better off. There are a bunch of solutions out there in the market. But if your scenario is the next 2 minutes, the next hour, there are very few solutions that are able to do that. The commonalities there are, again, as I mentioned, there are many high-speed data streams, the patterns that change rapidly, and it's too fast for the human analyst or the human action, in a sense. And last but not least, you need to be able to take action very, very rapidly. So that's what we focus on, and I'd love to take more questions later as we go. Well, thank you so much.
Rami, thank you very much indeed. And I'm sure some people are going to be very interested in some of the algorithms used there as well. Maybe we'll get a question or two out of the audience on that topic. But we have a third panelist with us as well, and Dutch Mcdonald, please come up and tell us a little bit more about what Maya does. And I know you've brought some rich media with you as well to entertain us.
Yes. I don't have slides, but I have these things called note cards, which are really nice. My name is Dutch Mcdonald. I'm the Chief Operating Officer at Maya Design. Maya is a technology design and research lab, and we really focus on the intersection of information and people in this emerging information ecology. We're about 22 years old. We spun out of Carnegie Mellon University, the Pittsburgh campus, not the Silicon Valley campus. And really from the very beginning looked at interdisciplinary collaboration as a way to understand people and information. So we hire and have practices within the organization. We have human scientists, so ethnographers, researchers, anthropologists, really, and cognitive psychologists, really trying to understand the context and the cognitive abilities of the people that we're designing for. We have an engineering group, so computer sciences, data scientists, mechanical engineering, and we have a visual design group. The visual design group really, they're looking at data visualizations, they're doing interface design, human-computer interaction, graphic design, industrial design. But in that intersection, we're trying to really understand and help our clients understand how to thrive in this emerging information ecology, and how to really think about what are the needs that what are you trying to solve for the end user, for the person you're designing for. So I think some of the things that the other panelists brought up are really interesting in the sense that there is this kind of way of letting machines do what machines are good at, but let humans do what humans are good at. And that's really what we help companies do. We practice what we call human-centered design or design thinking, so you guys are probably familiar with that terminology, but again, really putting the person in front and seeing how we can bend technology to the way normal people can interact with that data. Our sort of shorthand for pervasive computing is the word trillions. We've published a book, and I'm going to show a video right now that kind of gives our bent on pervasive computing world that we're going to see soon. So you can do the video. Is that okay? That's it.
I'd like to take you on a bit of an expedition into the history of computing, and I'll end up by talking about one unseen but very important part of the future. If you looked at computing in 1900, it was a career. A person who tabulated numbers was called a computer. Fast forward to World War II. We're creating massive, building-size electronic computers. Our goal was to break ciphers like Enigma, to figure out enemy activities, to save the world from the Nazis. In that era, there were very few electronic computers. This was just a small hill. It was really computing as 4 or 5 big calculators. Fast forward to the late 60s and all the way up to today. That's this mountain that we're on right now, and it's big. It started with this idea that you could look into a computer screen and see a place. You had a desktop and some folders and a trash can, and the information was actually in the computer. Today, at the top of this mountain, we have just passed 1 billion internet users. But there's a much bigger mountain ahead. The future isn't going to be billions, but trillions of computers embedded in just about everything. So how big is a trillion? Well, let's count back in seconds. Go back 1,000,000 seconds. That's like maybe a week and a half ago. Go back 1 billion seconds. Well, that brings us back to the mid-1970s. All right, now go back 1 trillion seconds. How far back do you think that is? Well, you know, it turns out that it's over 30,000 years ago. So trillions of computers. And this is not computing as a place or computing as a big calculator. It's going to be computing as an ecology. It's all around us, not information in the computers, but people in the information. I don't mean trillion, by the way, like the way we think about the big deficit. That's about 1 trillion $1 bills that are all the same. Not some things that are all connected or sending you spam or infected by a worm or asking for today's update. This is a big challenge. This is going to create whole new industries, and other businesses are just going to disappear overnight. So why do I say that? Let's go back to the current mountaintop. Many leaders see the mountain ahead. After all, it is huge. But many of them have confused a good view for a short distance. They try to get to the other mountain by building fire towers and rickety bridges in the hopes that they can get there from here using their existing ways of thinking. But they can't. You really have to climb the other side. You've got to start designing for trillions. It's a totally different and bigger challenge, frankly, than humankind has ever faced. But even though we haven't solved the problem of trillions, nature has. Your own body has trillions of cells. It's a complicated information system in its own right. In your body, you have atoms, which make up molecules, which make up cells, which make up organs, and those make up systems, which make up you, and then we together make up us, and groups of us make up communities. Nature uses layered complexity, and it also uses some other proven building blocks. They're all unseen, they're invisible, but there's no doubt that trillions are possible and represent the future information age to come.
Nice.
So true. So our goal is to figure out, how does this future of pervasive computing play out in the age of trillions for real people? Will they be overwhelmed by the sort of complexity that this could possibly introduce, or will we be able to design things that actually make people's lives better?
Dutch, is that video online? I think you
It is
told me
online.
it
You can
was.
see it on, if you just Google trillions and Maya, it's on Vimeo and
Or we could even use
Everywhere.
Google and search for it, I'm sure,
you
if
could
we wanted to do that. Very good. Thank you, sir. Thank you for that information. That's good. I can clearly see how design plays a big part in this space, and I'm sure you're going to talk more about that later on if we get some questions from the audience. But Ian, let me just begin with you, because when you were speaking, I jotted down a few notes here for myself, and one thing that I personally couldn't understand, so maybe you can elaborate a bit more on it. You said that maybe there are some boundaries, some error boundaries around some of the issues that you've got going on for the data. How would you actually define that, or how do you even work out what a boundary is?
Yeah, so that's a good question. Actually, there are a few questions here. So first of all is probably how you define what is an error, what is a reasonably error for a particular computation. And that can be, you can do that in different ways. One way is to say, like you do today, when we operate all those devices and services which have errors, is to define a very small error. Say the error is 0.01%. And that's your tolerance. And for most applications...
I was focused on the plus or minus 2.5 pounds on the personal scale, by the way, not the 2%.
Yeah. So that's one. The other one is to define with respect to the input. If the noise in your input, you say, will result in an output with an error plus minus 2%, no matter, even if the computation is exact and accurate. So if you have these measurement errors and things like that, then you can define your error, the computation error, to be a very small percentage of that input error. That's a different way. So that's answering the first question about how would you go about defining these errors. The other question is how you compute these errors. And actually it turns out that computing these error bounds is far from trivial. For some operations like counts, like this is what when people give you the poll, when they conduct a poll, they just count, right? How many people voted X, or they would vote X or Y, and then they give you an error. So there are some kind of computation for which you can easily compute that. But for other computations, like machine learning algorithms or things like that, it's much harder. And that's, again, it's an active area of research. Actually, we are conducting in Berkeley about how to compute the error bounds, because that's a key, right? If I give you an approximate results, if I just tell you that it's approximate, how you are going to use, I have to tell you also what is this kind of error in order to make that result usable.
Cool, thank you. And Rami, if I can just move to you for a second, because you probably skipped over this deliberately in the slides, but I'm going to ask the question anyway, because it looked like the crown jewels of what you were doing was really around some of those algorithms and the AI work in there. So how does that compare with other options in the industry, even things like some of the neural networking technology that's out there?
Yeah, we get this question pretty often, actually. It's a really good question. First, the topic of neural networks obviously has been around. It's whole science around it. Two key differentiators for us. We're not a neural network company. Some of the principles that guide our technology come from or influenced by it, but two things that happen with neural network consistently. One, they're very difficult to set up, and therefore they're not really useful in many situations. And with Grok, you don't have to set up anything other than know where your data is, pretty much. So the setup itself and the variables behind the scenes that the system optimized for and so on are transparent to you as a user. And the other thing that is probably more critical as far as the type of problems that we deal with, neural networks are very good when it comes to spatial type problems, which have to do with classification and clustering of information. And what we do that, but we also do it with the temporal sequences. So neural networks don't really do well when it comes to kind of time series problems that are so relevant for high velocity data streams. And so what we do is we actually create we have our own algorithm that I'll be happy to talk about, and which we just, by the way, announced its availability in the open source as well. And so people can actually experiment with it, but it's designed for time series data, which by definition is stream.
Does it have a name, the algorithm?
Yes. So
the Grok algorithm?
No. So the algorithm itself is called the Cortical learning algorithm, and that's again going back to the nature, and I was glad to see the same analogy of using nature. But we just released it on numenta.org, and it's called the algorithm. The project itself is called NUPIC, N-U-P-I-C. And numenta.org has the information about the open source activities around that as well.
Very good. And let's stick on the time angle as well, Dutch, because you showed that very interesting and fun video, I thought, comparing millions, trillions, and billions in terms of time. I actually showed it to my 14-year-old so he could understand what he was talking about when he said he wanted to be a billionaire when he grew up. It's going to take you more than a week to count to a billion, I said. Better get going now. Well, I was only doing a billion. I didn't even think he'd be a trillionaire. I was, I'd like my kids to be billionaires, but trillionaires, come on. That'd be good enough. Having $5.50 would be good right now.
That's right.
Anyway, enough of that. So, but if we go back in time, in the last decade or so, have you seen, Dutch, much change in terms of the people coming to you asking for design ideas, asking design questions?
Well, certainly, design thinking is in the press, everyone's talking about it, but I think really where we've seen changes is a lot of our early businesses with the government. Actually, our first client was with digital equipment, if you guys remember digital.
We're in the Computer History Museum,
I
remember?
know.
So of course we remember Digital Equipment Corporation.
I saw them down there, yeah. But we did a lot of work with the government and through DARPA, and so we were looking at how to augment the cognition of warfighters so they can make decisions on the battlefield. And so really giving them just-in-time data that could help them make good decisions. So a lot of that early research around how we think about taking large amounts of data and making it actionable information out of it came out of that research. But really in the past 10 years we haven't seen much of that, and most of it has been through basically consulting work. So we do consulting in a bunch of different industries, work for hire, but we also, unlike some design consultancies, do internal research and development. So we have a research team right now looking at decomposable computing, how to make very, very tiny bits of computing power that can be placed throughout the environment. They can both have inputs and outputs. That's something we're incubating, but really we feel like having our own research arm versus the work for hire has allowed us to get deep into this idea of pervasive computing.
Interesting. And I can see a few people moving around in the audience indicating they've probably got questions, so we'll do that in a second. But if you've got a question, just ready yourself now, but I'm just going to do one more here because that kind of led me on, I thought, to a different thing. Dutch, let me stick with you as you were already talking about that change in the last year, but have you also seen a change in the kind of people coming to you? IT departments, marketing, for example, different kinds of people? And do you think pervasive computing has made a change there?
Yeah, traditionally, product development, I use product very broadly, so, software products or services, service design, was really coming out of either engineering or the product development group or a lot of labs like yourselves where they're doing some research. But what we've seen lately is, particularly around the data visualizations, the data sort of analytics we're doing, is that the marketing organization is very, very interested. So the chief marketing officer and the CIO are getting together all the time because the IT side may not always see the value in that data, but the marketing side really wants that data. So, with the marketing,
they want it more quickly as well, I'm
and they
sure,
want it very, very quickly. So this kind
add.
of data at the, what did you say, data at the speed of light or data?
Yeah, that's one of our things with fast data. Yeah.
Right, and the really fast data. And so they're using it in a very, very different way, really replacing things like voice of customer and things like that. But,
replacing the voice of customer surveys? Come on.
Yes.
That'll never happen.
With real, and when you think about it, when every product has some little piece of computing power in it that can tweet or talk, or you can track and know where it is, like your bottle of water, I mean, that's valuable data for a company to know. Where's my product? How's it being stored? Is it being stored properly? But the question is, where do you see the data patterns, and how accurate does that data need to be to make actionable decisions?
Yeah, and maybe if we run out of questions in the audience, we'll come back to what good having a chip in a water bottle is to a consumer, and we can ask that question, because I can imagine how useful it is to a big company like Nestle, but as a drinker of the water, I'm not so sure why I care that it has a pervasive computing device in it.
Floating within, yeah.
But there you go. But that's we'll ask that question later. So who would like to go first with the very first question for the panelists? I was told earlier on that the left-hand side of the room has a lot more questions than the right-hand side of the room. So sticking to that, all the right-hand side is looking really angry. And in fact, sir, on the right, at the back, we have the first question. I believe you need to wait 2 seconds for the lady to run to you with the microphone, unless you have a giant voice like me and can shout. We'll wait for a second. Away you go, sir.
I have an answer to your question. What user wants to have a chip on the bottle cap? There is a company that's providing instrumented medicine bottles, and they're particularly useful for elderly patients who forget to take their medicine. And what happens if you don't open the bottle and take your medicine, you get a phone call. And it reminds you, hey, it's time to take your medicine.
So I think that was an answer to my question.
Yes.
Excellent.
So there is
Not even on the panel.
There is a person who wants the data. Your question was the manufacturer
Yes, sir.
wants it, but why would a person want it? That's an example of why a person would want the data.
So panelists, let's do this one right away. So does anyone else have an opinion? Pervasive computing is out there. We've got one great answer, medical answer basically in terms of life expectancy of the device. Is that really what that was? Do it again a bit. So it's a little hard to hear you.
So you have you go to the drugstore, you give them a prescription, they give you a medicine bottle. In the cap of the bottle is a chip, and it has a wireless connection, and you have a port, an access port in your home, and when you open the bottle, it sends a message to the access port. The access port's connected to your medical service provider. The medical service provider has your schedule of medication. If you don't open the bottle, you've forgotten to take your medicine.
Very good.
Then you get a telephone call from the service provider reminding you to take your medicine. So it's not the manufacturer of the medicine or the bottle who's interested, it's the patient.
The consumer themselves. Very
Yes.
good. So panelists, do we have any other good examples like that of consumer benefit from pervasive computing?
I can talk about what I think the overarching trend is, which is right now we think about analytics in terms of big decisions that we need to make as a business entity or as a person. And I think that where we're going with pervasive computing and M2M scenarios is more about many, many little millions and trillions of mini decisions that are made by machine-to-machine type context or scenarios that don't necessarily lend themselves to how we think about it today. Today we think about big monolithic applications, big boxes. We think about decision time horizons that have to do with weeks and months, and that's yesterday's analogy. The future, and even going back to the notion of self-driving car, it's all about processing data real time, analyzing the streaming information, making the right decision every second, every millisecond. That's something that you'll see in so many industries going forward, and I think that feasibility is simply a question of time, and these scenarios will present themselves very quickly.
Ian, do you have
actually, following it's an analogy, right? It's a very clear analogy, and you want to use it as an example or not, but it's there. It's ad placement, ad targeting, right? It used to be, and it's still, in some cases, you negotiate, an ad campaign every 6 months for particular shows, for particular demographics, right? But now it's ad targeting. What ad targeting means, it's about personalized decision. The same thing is actually in medicine, right? The medicine, and actually this is one of the most exciting developments. The new thing is about personalized treatment or precision medicine. That's kind of the name, which takes into account not only your clinical history, but your DNA and so forth.
But I think those sort of things really kind of make the business case. Like, you can understand it from the business standpoint, but the consumer, that was a good example about, a service that could be valued by the consumer. But when every water bottle or cookie or bag of chips has a sensor on it, what's the value to the consumer?
It can suggest you see how much you like based on how much you drank.
But that's a good benefit to the vendor. I'm sure Nestle wants to know how much I'm drinking.
It will recommend to the consumer something you like.
I
you never knew about that.
I agree with Ian on that, because I think that you're bombarded anyway with commercials.
Yes.
99% of them are irrelevant. I started getting, I don't want to Facebook great company, you love the product, but I get, on my timeline, things that are like, seriously, you should know me better. I'm completely not interested in these things that you bombard me with. So the better you optimize, based on who you are and what you need, the more relevant it becomes to you.
Or it can be, again, how is that information is used? Maybe it's used by Nestle for more targeted and better commercials or ads. That's one. But you can think about that this can be used to enrich your profile and behavior, which can signal, some health, maybe issues. Again, how much you
I also
drank,
think
but-
sort of another thing, I mean, that's absolutely true. But another thing is that something that you get as the consumer is sort of transparency, or maybe even wicked transparency. So in this age we're talking about, nothing's hidden, right? You can't hide behind the marketing, campaign that's put out there, because people can get to the real information. They know where this bottle, can find out where this bottle's made, not right, maybe even the exact location of the plastic that's made
And we
out of
even
it.
know that the
And you
source of the water is the public water supply of Sacramento, California. Very useful.
That's right, but in that age of transparency, it empowers me as a consumer to make choices that align with my lifestyle. So if I don't want to buy a bottle where the manufacturer uses children to manufacture their products, I can choose to do that because I know it. And we've seen responses to that already, campaigns where marketing organizations respond to that.
Excellent. Well, we took 11 minutes on the first question, so let's try and we're going to keep it going. We're going to keep it going. Left-hand side of the room. Do we have any questions from the left-hand side? Sir, at the very front. Excellent. Thank you very much. You'll have to wait a long time for the lady to come with the microphone. She's way at the back of the room. And I'll repeat the question if people can't hear it, because it sounds a bit funky.
Sure. In fact, I'm very curious
You're
about
very
the
loud.
consumer side of things, because I just wonder to what extent the technologies, the computing power you're talking about, when those will be available more at the consumer level. As Eon pointed out, there's a lot of data that's disparate. It's not sharing a common schema. And one of the biggest challenges that people, especially even including those in the quantified self movement, have is that they're collecting enormous amounts of data on their own self, but the tools to allow us to visualize and analyze this data are incredibly lacking. I'm just wondering to what extent and when might such tools that you describe be available for the rest of us?
Well, we're open for business, but I think that you said something which I think was very, very profound, if you allow me to respond to that, which is you said, when will we have the tools to visualize and act on the data? There's so much data, and it's so frequent that think about it in terms of how I visualize it and what action should I take is probably the wrong question to ask. The question is, you need to start asking the question, which action could be automated so I can actually take advantage of these high velocity streams? Because there's no way that you and I can keep up with that as human. We're not designed for that. And so we had the discussion earlier over lunch about, I think it was a library example that you gave. So much written content out there, and sometimes all you need is a snippet of information versus reading a whole book. I mean, it's really impossible for you to keep up with all the digital content out there. Now, if you had the ability to isolate the snippet of information that is relevant to you in a given moment, Google, Wikipedia probably are good examples, then it's a step in the right direction. It's the same thing that has to do with the content is being aggregated, data that is being aggregated, and you can't act on it. So storage is not the solution. Visualization is not the solution. It's how do you act on it.
Yeah.
I would amplify that. I think that when you look at the cognitive load of an average consumer or any person in this room, you can't spend that time. Richard, you were talking earlier about how you had your smart meter and you looked at it the first week every day, and then
I remember
every 3
religiously
months.
looking for the first 2 weeks. That was a year and a half ago.
But after a while, you don't really have the time in your life to do those sorts of things. So
I do have the time. It was just very boring, the information as well.
Exactly.
And you didn't have an action to take either.
Thank you. That's correct. I have no action to take on that data.
But what we're saying is, in this world of pervasive computing, let the machines do what the machines are really good at, and let them, when you need that information or you need to present it. And I think those are the interfaces you're talking about. They're yet to be designed, actually. And but we know we have to start with what problem are you trying to solve for people, and bubble up those answers and let the machines do what they're good at.
Yeah, I think you need everything. I mean, in all the fairness, and I think yes, it's a huge amount of information. Actually, everyone collects today data, and you hear more and more often saying, "Okay, I have all this data. I'm not doing anything with it. So what can I do with it?" And typically, yes, you want to make decision and you want to automatize the decision. But the truth is that to get there, what happens? People have to understand a little bit of data. There are people trying to understand what kind of decision I want to make, right? So it gets an inform what kind of data I have, right? just applying, it's not always magic, just applying a very smart algorithms on the data. I work in several examples and applications, and guess what? In many cases, actually, the data was dirty, but it was dirty because they didn't have the semantics expected by the algorithm. You look for one value, it's a different value, right? You have different version of the software. The semantics of the fields may change. You need to factor that in your new generation of software and so forth. So it's much more complicated. I think that there is a side, and for people, and this is what people try to figure out, what kind of decisions they make, and for that, interactive analysis and visualization are of great use. Yes, I agree that in the end, you are going to go to automated decision. But it's very hard to just jump there, at least for new fields or new applications.
How many people in the room, I'm just curious, would know which algorithm to apply to a given data set? By show of hands. I'm just curious, how many? Yeah, I mean, that's probably a couple, but that's the whole point about the explosion of data that's generated by machines. How many data, I mean, we talk about data scientists, and there are not that many of them who really know their way around the algorithm, whether you need to use random forest or KNN or SVM and for which data type and so on. You got to take all that out of the equation because it simply doesn't scale with the explosion of data earlier to your point.
Very good. So let me just interrupt 1 second. Let me finish with just one open panel question, and maybe Rami will carry on with you as you were already speaking. It seems that some industries are going to be pretty adverse, I'll remove that word, pretty disrupted, maybe not adversely, but changed certainly by what's going on here. So I can imagine a few industries off the top of my head, but what do you think from your company's point of view or personal point of view those biggest industries that are going to be disrupted are?
Well, I think by definition, going back to the notion of action, if you're able to take action on fast data, then you want to be disrupted by it. And I think financial sector probably comes to mind, the ability to act on a millisecond based on changes in ticker, trading volume, and volatility of stock price and so on. And so that's what Wall Street is doing and has been doing for a few years now. I think energy management and its derivatives, anything that has to do with high value assets such as jet engines as examples, telco comes to mind, some retail scenarios, especially online scenarios in terms of customer churn and things that have to do with the immediacy of serving a customer. These are the industries that would lend themselves well versus slow-moving industries where the action could, if I'm not going to take action next week, nothing's going to happen anyway. They're not going to be disrupted because it's not their scenario, but someone will probably figure out a way to disrupt that industry and take advantage of that speed.
Dutch, do you have any thoughts on that area that you want to share?
Thoughts on that area? Yeah, I mean, I think, it's interesting because we do work in a lot of different sectors, and I can't really predict which are going to collapse and which industries are going to rise.
Well, I shouldn't have applied adverse disruption. I guess it could be a positive disruption as well. It doesn't need to be collapse.
So, well, you did say it. You said adverse first.
I know, but I didn't mean to.
But where we see some really interesting things are in consumer packaged goods, where people are really looking at how, like P&G, for example, looking at how to embed some computing power in there. Things like some of the household appliance companies are doing some very interesting things right now. We're working with electronic medical records. Now there's an interesting space where there's a lot of data being collected, but the people that say they want the data don't actually know how to make actions around them. So we're working with Epic right now to kind of figure out what kind of data does a doctor need versus a patient versus a nurse versus the housekeeper for the hospital. And so I think those that are taking the data and trying to say, how can I solve a problem and make our operation better, the ones that are going to survive.
Excellent. Thank you. Ian, do you have one final industry to disrupt us with at the end?
I think that almost every industry will be disrupted over the next 10 years. But I think that one I want to emphasize, I think it's healthcare.
Healthcare?
Yeah, I think that it's ripe for big disruption, and probably everyone care about that as well. And if you look at, for instance, cancer treatment. This will become more and more important. Why? Because more and more people will get during their lifetime cancer. Why? Because we are going to live longer and longer, and then it's more likely to get mutations. There are some people predicting that, 1/2 of the men and 1/3 of women will get.
Panel, thank you so much. We are out of time. Ian, I have to cut you off as well. I've got the big hook here on my left about to get us off. Thank you very much for being on stage, and thank you, everyone.